Good morning, everyone. My name is Mike Brown. I'm a Keysight Major Account Manager for the Southeast United States. And today, hopefully you are here to see a talk and a webinar about coexistence of 5G with other technologies. Some of those could be radar and satellite, but I think this could also be applicable to other technologies that use spectrum. So I'm going to hand it over to Chris. If you want to introduce yourself real fast, Chris.
Hey everyone, my name is Chris Pineda. I'm a staff engineer in the Mid-Atlantic region, working closely with Nick Buonamico and Andrew Stiegler, who some of you might have worked with in the past. So if anyone has any questions or follow-up, please let me know. And please remember to fill out the survey at the end. Thanks, Brian. You can take it away, please.
Brian,
I don't think we can hear you, Brian.
Yeah, we're not getting audio, Brian.
You're still on mute.
Sorry about that. Is that better?
There you go.
Yes,
There
gotcha.
you go.
Good morning, everybody. This is Brian Kay. I'm an application engineer out of the Florida office, and today we're going to talk about 5G coexistence with satellite. We do have a chat, and we also have some poll questions that we're going to be putting up. Do we want to go through one of the poll questions now, Leslie, or do we want to hold off on that? Or
I can put one of them up right now.
Disable my video here just so we maintain good bandwidth and for the slides and so forth.
I've launched the poll for you, Brian. I'll keep that up for another couple seconds. Okay, I think I can bring that down now. And there's the results.
Okay.
There you go.
All right, so are we all set to move on here, or?
Yes, you are.
Okay, so we're just going to get right into this, and I think we do have another poll question later on in the presentation. I just wanted to go through it. So again, we're going to be talking about 5G NR coexistence with radar and satellite. And I'm just going to move right into the slides here. So we're going to talk about, this is our agenda for today, the problem of coexistence, some of the metrics or measures associated with that, and then we're going to go over some of the test tools. There are some things that I have right behind me, and I'll show you the video later on, some of the lab testing and field testing that you could actually perform, verify if you have any coexistence issues. So we'll go through that as well. Got some background noise. I'm not sure if we can maybe mute the phone. There we go. So we're going to talk about some of the use cases here, particularly the 3 use cases associated with 5G. So we're going to start off with a little bit of a primer. And the first one is the enhanced mobile broadband. This is, I guess, the most popular one. This is where we're going to get to 20 gigabits per second. That's the theoretical throughput limit that they're looking at. These are all your cell phones and all your services associated with your Verizon and your T-Mobile and everything. But some of the other ones that are also associated with some of the key success factors in 5G are these other 2. One of them is the ultra reliable low latency communication, and the big or challenge associated with that is the 1 millisecond latency. So typically, or right now with a lot of the LTE and some of the existing, it's about 10 milliseconds. So this is a 10x improvement. So some of the technology associated with that, we do have some listed here, is the self-driving car. Another very popular one is this medicine. They're looking to do remote operations in the field. So basically a doctor in, hospital in the U.S. can work on a troop, overseas that may have been injured, and they could actually perform a remote operation. And as you can imagine, the remote operation is going to be utilizing robotic arms. So you don't want to be able, you don't want to have any latency associated with that type of procedure. And then this one's the most massive machine type communications kind of taking a back seat a little bit. So that right now they're kind of focusing on these two. This one's out there, but that's being served pretty well now with all the IoT technology and some of the LTE stuff. So this has to do with, some of your smart meters in your house where you may want to go in there, not a lot of data throughput. The key with this is the battery life. It has to last 10 years, and it has to be able to support what they call instant on, instant off. So when a car drives down the road, wants to read your electric meter, it's got to come on fast, read the data, and then shut itself off again in order to maintain that 10-year battery life. So again, that's kind of being serviced now with some of the IoT and LTE that's existing out there. So these are the two critical ones right now. Again, there's a lot of bandwidth being utilized. The enhanced mobile broadband is 5 to 20 gigabits per second. That's theoretical. Not sure if they've actually ascertained that yet, but that's the theoretical. And you can see that some of these have a different frequency range associated with them. Some of the massive machine stuff is all low band, less than 3 gig. The ultra reliable with the 1 millisecond is actually using some of the 6 gig band and also higher bandwidth as well. So this is a breakdown of all the bandwidths. So one of the things I wanted to highlight here is what's associated with 5G NR. So anytime you see an N in front of the number, that basically correlates to 5G NR. So, there's a lot of bands out there, as you can imagine. And, but when you see the actual N in front of that number, that basically specifies that this is a 5G NR band. So just FYI here, some of the more popular ones that's being utilized for what we call 6 gig and below is this 3.3 to 3.8 gig because you have 500 mega bandwidth. So just based on what I'm seeing, just thought I'd share some. They're looking at utilizing that band. It's actually called an old CB band that they're trying to utilize here for some of the less than 6 gig communication. And then over here, you can see the N261. We're going to highlight that. That's basically the 27.5 and higher to talk, that's basically utilizing the KA band. So that's where the coexistent issues are basically going to arise when you start communicating 5G NR services with the KA band of 28 gig. So again, just some background here. So there's two ranges, I guess you could say, or frequency ranges that people will operate in 5G. And this will be one of the, as an application, and you asked me for test equipment, one of the first questions we're going to ask you, and Mike Brown as well, and everybody, are you doing FR1 or FR2? Okay, so I just want you to be familiar with that phrase. FR1 has a frequency range of 410 megahertz to 7.125 gigahertz, and that is a little bit higher. It used to be 6 gig, but they bumped that up a little bit. And here are the actual band numbers, 1 to 255. So it's not just sub 6 gigahertz anymore. It actually extends up to 7.125 gigahertz. So anytime they can get broader bandwidth and they can push this envelope in frequency a little bit higher, they're going to do it. The other thing we're going to be specifically talking about is this FR2 band, which extends from 24.25 to 52.6 gigahertz. I guess the two popular ones that we're seeing out there, your AT&T and Verizon, is the 28 gig and the 39 gig. Particular interest is the 28 gig. I'm going to be highlighting that today because, again, that is associated with the KA band satellite frequency. Channel bandwidth can go up to 400 megahertz. So this is basically the bandwidth of the signal, you know, the data bandwidth. Some people call it the channel bandwidth. You'll hear different terminology. Some people call it the 3 dB bandwidth, things like that. It also supports beamforming. That's one of the other features associated with that. You know, years ago when Verizon or AT&T deployed a antenna system, you know, they physically would go up there and turn, you know, this chain that was attached to the antenna, and it would actually physically steer the antenna to get the proper coverage. Well, you can think of that beamforming as, you know, we're turning that beam electronically now. So using, you know, in what they call antenna coefficients, we can actually steer that beam electronically, and you can do that dynamically. So let's say you have a, you know, a Super Bowl coming up, and you need to point, you know, a lot of beams towards that dome or that stadium, you know, to cover that Super Bowl. Well, you could do that, and then after the Super Bowl is over, you could go back and set it up, do your basic coverage again. So, you know, it gives a lot of flexibility as far as, you know, what I call steering bandwidth or steering throughput dynamically. Again, just a comparison between FR1 and FR2. The maximum bandwidth you could have in a sub-6 or a sub-7 gig is 100 megahertz. You could have a maximum number of component carriers of 8. So you could actually have 800 megahertz associated with that. And there's also a numerology. This has to do with the carrier spacing. And in addition, the subcarriers, the new FFT bandwidth is up to 4 kilohertz, and the subframe length is still 1 millisecond. So you see a commonality. The difference here is the FR2 can have up to 400 megahertz of carrier bandwidth, and the main reason for driving this is really to get this bandwidth. You know, in order to get that 20 gigabits per second bandwidth, you know, you're not going to be able to do that in the standard channel bandwidths that we have out here now. Many of them, the legacy channel bandwidths are 15, 10 megahertz, and that's it. So there's no way you're going to get that type of throughput with those channel bandwidths. So they've opened up this spectrum, and again, the two popular ones are the 39 gig, which has, this is saying 3 gig, I thought it was more like 1.4, and the 28 gig, which has 800 megahertz. So again, these are the FR1, so you can see that you can partition the channel bandwidth to suit your particular, you know, what do you own? Like, you know, if you only own 10 megahertz of bandwidth, then, you know, you could broadcast a 5G signal, you know, and set it up to generate a 10 megahertz bandwidth. So in many cases, a lot of the existing infrastructure can support the 5G NR. You know, you just can't utilize 100 meg. You may, you know, if I only own 10 meg or 15 meg of bandwidth, well, I'll use that and I'll broadcast 5G over that bandwidth, you know. And there's also a new technology coming out that talks about what they call DSS, where they're dynamic spectrum sharing. So if you have a 10 meg signal, 5 meg can actually be used for LTE, and the other 5 meg can be used for 5G NR. So that's a little new technology that we're starting to see. And then the 5G, we got some questions coming.
Yeah, we had a couple of questions in the chat. So before we move too far ahead, I thought maybe we could just take a minute or two. Do you have the chat in front of you, Brian, or do you want me to read them to you?
I do have the chat. I'm trying to expand the window, but I'm having problems here.
I mean, I can read them off to you. It's not a big deal. So we have a question. Number one is, what are the restrictions in the FR1 band? And the addition to that is because that band covers a lot of safety related bands. So I think they're talking about, you know, public safety radios, that kind of stuff. Can you address that?
Yes. So the FR1 bands, pretty much it's 410 megahertz up to 7.1 gigahertz. So the restrictions are really pretty much what do they own. So I kind of just highlighted that here during this discussion. So I think I partially answered it just recently here. So
Okay.
if you only own 50 megahertz of bandwidth, like a band 13, or a band 5 or something like that, there's a limited. The FCC says you got 10 meg, then that pretty much dictates the maximum bandwidth that you can support. So that's the main reason why the channel bandwidths go all the way from 5 meg up to 100 meg in size.
And then there's one other question, which is when you're talking about the bandwidths, is that before carrier aggregation?
Yeah, these are, you could have multiple carriers. So if you own 15 megahertz of bandwidth, in reality, you could actually set up 3 5 megahertz carriers, 3, concurrent contiguous carriers if you wanted to. So you can break up, for lack of a better word, this channel bandwidth into smaller carriers if need be. And a lot of times, the reason for that is driven by, the phone. What bandwidth does the actual UE support? The phone may only support 10 meg or something like that. So why would I allocate 15 meg to a UE that only supports 10 meg? That's an example there.
Thanks, Brian. That's everything in the chat for now. For the folks who asked those questions, if you need any additional clarification, just go ahead and drop that in the chat and we'll continue to monitor. Go ahead, Brian.
Okay. So again, some of the new operating bands, you do have some of the ISM bands. I think somebody just mentioned those. Again, the popular one is the CBRS band. This is an old CB band, and it extends from 3.3 to about 4 gig or 3.8 gig. So you can see that, with this new band, they have a much greater bandwidth. They can actually fit a 100 megahertz signal inside that frequency range. So that's really, as far as the FR1 5G NR, a lot of companies, Sprint and so forth, are really looking at utilizing that specific frequency band to get the throughput and the, basically provide the wider bandwidth up to 100 megahertz. As far as the 28 and 39, again, those are the 2 popular ones. Some of these 71s and higher are used in a lot of the automotive radar technology, which we're not really going to go in today, but just the FYI that the 71 and 76 gig is used in a lot of the automotive radar technologies, collision avoidance and things like that. So, any questions on that so far?
I don't see any other questions right now, Brian, so I think you're probably safe to move ahead. I'll jump in and let you know in another 10 minutes.
Do we want to do another poll
questions
now, or did you want to wait on that? I might have done too many slides down for the second poll question here.
Yeah, I think you can continue on.
Yeah, go ahead. And I think
going.
you're fine to just keep moving ahead.
Yep.
Yeah.
Okay. So the 5G NR FR2 overlaps basically a lot of these 27.5 to 20, to 28.35 gigahertz. So there's some spectrum sharing going on. So in many cases, the base station may actually use the lower band, like 27.5 gigahertz, to set up their actual communication link. Obviously, you can't go up and change our satellites. They're what they are. So the base stations have to adjust accordingly to make sure that they get the throughput and they don't do any interference there. So it's important to make sure that the fixed satellite services are not interrupted at all during communications. So again, here you have the 3.5 gigahertz. That's the popular band that's being used for less than 6 gig. You also have to be concerned, a lot of these satellite dishes, they have what they call an LNB in them, which is basically a block down converter. So you also have to be conscious of the block down converter. So if the block down converter converts it down to a 3 gig signal or a 2 gig signal, you also need to be conscious of that. So the FR1 testing is just as critical in some cases to make sure that that's not interfering with any of the post block down conversion frequencies as well. So a lot of customers will actually, they'll have a satellite dish, and I did this with one of our Cablevision customers, and we just took a van and we drove around with the van, and we were just, generating, blasting out this 5G signal, and we just created concentric circles further and further away and closer to the signal, and they were monitoring things like RSSI and other parameters on their receiver to make sure that it wasn't interfering. So this is kind of the scenario here. So think about it, is you have this 5G base station, and in many cases you have the satellite ground station, and they need to make sure that this is co-located so that this doesn't interfere with that signal. Now, the good thing about this is with the beamforming, you can steer the beam in different directions, but if that may limit your coverage. So you can steer beams in different directions to avoid interrupting that ground station. But, if there's a bunch of houses and people living behind that, that could definitely reduce the actual coverage that you have. So, and again, you got to remember these signals coming down could be, extremely low power as well. So this is the concept here. You have this signal generator that creates this DVB signal, and then you have another signal generator that can actually generate the 5G NR. You combine the two together, and then you could actually run it through the LNB and the bandpass filter, and just look at your satellite receiver and also look at the signal analyzer. Sometimes people will just couple this off so you could actually see the spectrum, going into your satellite receiver, and you can pretty much determine, okay, what power level will actually start to corrupt the communications on the satellite receiver. So here's an exact picture, and it's kind of showing real time what's going on here. So this is a 5G signal on the left, and this is actually a satellite communication. So you can see right here we have some guard band so that they can, both happily live together without interfering. And so here you can actually look at the 5G demodulation, and the key parameter, I think it's on the next slide here. You can start to see the constellation. I'm going to go into more detail on what this constellation represents. But you could start to see how that when you start moving these two carriers closer together, you could definitely see that, one's interfering with the other and causing either high, bit error rate or packet error rate, and, just reducing the quality of the communication path. So you can see here on the edge, what they're showing here is in the OFDM environment, you have multiple subcarriers associated with this. So you can think of it as this entire spectrum is really the sum of individual tones, all contiguous or next to each other. So let's say you got 1,000 tones right next to each other. So you can start to see that as that other carrier starts interfering with this one, you'll see the upper carrier starting to cause higher bit error rate or EVM issues here. So this is a great view to actually show you, okay, where in my spectrum is that interfering, causing problems. I want to know exactly, is it in the middle, is it on the left, is it on the right? What's messing up that constellation? So this view allows you to determine that, okay, I got something just to the right of me that's messing me up. So I either need to move my signal to the left or do something to make sure that I improve that quality of the signal. So a little primer here. Error vector magnitude is the key metric or measure that we look at to determine the quality of the signal. And EVM, you can also tie that back to signal to noise ratio, bit error rate. They'll kind of all correlate together. So the 3GP specification, develops a specification. So if you're using these different modulation schemes, this is the EVM performance that you need to have in order to guarantee a certain performance, throughput. So EVM basically, just a quick summary here, is basically the relationship between the measured vector, which is what I basically pick up on my spectrum analyzer, versus the reference vector. So this reference vector is basically, you think of that is modeled. It's done, it's math. Okay, we actually generate this vector using math. We build that. You can almost think of it as like a modeling software tool, and we create that perfect vector, right? No noise, nothing. The actual measured vector can will definitely deviate some amount from this perfect vector, and it can deviate it either as a function of phase, which is what we're showing here with the blue line, and or amplitude. So you can see here that this measured vector has slightly higher amplitude. So things like amplitude modulation can cause this vector to go higher. Things like phase noise or some type of phase interference will basically make it move this way, horizontally. So, and this error vector is basically the difference between the perfect vector or the reference vector that we calculate and the actual measured vector. So when you look at that on a constellation, the rule of thumb is, you'll hear the term, the tighter the dots, the better. Okay, so as you get more and more noise, the actual circumference of these constellation points, and these are all linear values, these are actually voltages, get wider and wider. So the rule of thumb is if you see this I'll use this one, if you see the constellation point move in this direction, that's some type of phase interference, okay? If you see this constellation point going in this direction, that represents some type of amplitude issue. So maybe you got some audio or something, power supply, something is generating, some type of amplitude interference on there. So just to help you debug this in a little more detail. So the way that a lot of these UEs and base stations work is they try, in the beginning, what they'll do is they have what's called adaptive modulation. So when they first connect, right, you actually set up a call, they're going to try to utilize the highest modulation scheme possible. So they're going to set it to 256 clam because that's going to give me my best data throughput. That's going to give me, the performance I really need. If they can't ascertain that, either because the signal to noise ratio is no good or we have some type of interference, it's going to start to back off. So it'll back off to 64 clam. Try that. That's still not good enough. So it'll just keep going down until it actually finds, a good quality of service. So the signal's got to get through. We got to communicate, and depending on what they call the channel, the quality of the channel or the quality of the connection determines pretty much which one of these throughputs. So in many cases, when you look at a lot of these modulation schemes, they kind of correlate to the number of bars you see on the phone. So if you got 5 bars, there's a good chance you're transmitting one of these higher modulation schemes, and you'll definitely see that everything just updates a lot faster on the phone or the UE. So discriminators, so there's frequency spacing, distance between the transmitters. Again, I told you one of the tests we were doing is we were actually setting up concentric circles around the satellite, and we were just driving further and further away and closer. We would start out further away, and then we would move closer and closer. And then we could actually determine, okay, if we want to put this base station, you know, in proximity to this, it has to basically reside, you know, 10 blocks away or some distance away, or else it's going to interfere. So, you know, we actually do field testing to verify, okay, where can we put this without messing up that satellite? And again, we look at things like EVM, throughput testing, power levels, and you know, antenna types, and so forth and so on. So as far as hardware to accomplish this, we have a variety of different signal generators available. So this would be used in many cases. Customers will use this, and then right underneath that, they may have an amplifier to actually boost the signal, and then they'll connect it to some type of horn antenna, and this way they can actually point the horn antenna either directly at the satellite and slightly away from the satellite. Sometimes they turn it, and they'll look at the RSSI on the satellite receiver to see what happens. Okay, if we face it this way, 30 degrees away from it, even though it's close, if it's 30 degrees away, it'll still be okay. So you can actually co-locate based on the phase and so forth and so on. So here's the, this has an M93. This has 1 or 2 channels, so you can actually see the 2 channels here. So what a lot of customers will do is they'll generate a 5G NR signal here and an interferer there, or they'll generate 2 signals out of 1 port. You can mix and match these to conform to whatever you want to set up. And then we have 2 flavors. This is one with a front panel, and this one is more of a you know, a chassis built where we have individual discrete plugins. One of the more popular ones, though, is the actual one with the GUI here, so you can actually click on the front panel. And this box will go all the way up to 44 gigahertz. So with one box, you could do both any type of 6 gig interference testing or 7.125 gig interference testing, 28 gig, 44 gig, and it will support all of the bandwidths. I think this has up to 1.5 gig or 2 gig of bandwidth as well. So this will cover you for all of the coexistence testing. And it also has some pretty good power coming out, but in some cases, customers may want to boost that up even more. So this is showing some of the actual diagrams that we have with our analysis tools. So here we're looking at a 28 gig signal, and you could actually see the constellation that's going on. You know, this is obviously a 0.78% EVM, so that's really good quality of signal. So again, the EVM performance is also related to the signal-to-noise ratio. So when you look at signal-to-noise ratio, what we're talking about is basically what is the ratio of the signal level to the noise floor. So if you look at this, this is 10 dB per division. So we got 10, 20, 30, 40, over 40 dB signal-to-noise ratio, which explains why the EVM is less than 1%. 40 dBm signal-to-noise ratio equates to about 1% EVM, so you can see we're even do better than that. That's a real perfect world right there. So we can actually, you know, dynamically create these signals using what's called the Signal Studio product. So we do actually have a waveform creation tool to allow you to actually generate both the interfering signal, and you could pretty much turn these on and off. The thing we're highlighting here is the actual channel response. So what we're looking at is what we call the quality of the channel, or you know, how good is the signal, you know, going from this signal generator or your antenna to the actual, you know, receiver, you know, satellite, and they call that kind of the channel performance associated with that. So as you can imagine, there's a lot of things that can, for lack of a better word, distort the signal. specifically what they call multipath effects. So when you're trying to transmit a signal from point A to point B, well, there might be a tree in the way, or a building, or, you know, this truck drives down, causing either some type of Doppler spread, or just fading, or just loss of signal altogether. So ideally, you want to have, you know, a clear line of sight between any of your base stations and the various, you know, UE devices that you're trying to talk to. So here you can actually see a base station effectively is talking to a car, right? Your car can have a 5G LTE signal in there. So all these different effects, you know, the shadowing, the fading, the path loss, you know, we can simulate those using what's called a fader, and we're going to show you that in a couple of minutes. So all these effects could definitely have an impact on the quality of the signal from the base station to the UE. So again, the multipath effects cause fast fading. So when your phase is jumping all around, and they're in the 5G, 3GPP world, one of the terms you're going to hear is what they call channel models. So when you look at a fader, you know, you can put in all types of loss, you could put some Doppler spread, you could put some phase shift, but how do you really know what to set that to? How do I really know what to simulate between the base station and the mobile? So the 3GPP actually defines what they call channel models. So you pretty much load in these models, and they'll apply the specific loss and fading and Doppler shift to simulate different types of mobility. So they have models to basically simulate, you know, a high-speed train, you know, going 300 miles an hour. They also have models that will simulate, you know, a person walking, you know, so they call these fast and slow in many cases. So the actual channel fading, in many cases, is already predefined in the spec, and you just basically, so with a fader, you would just load that channel model in and pretty much turn it on. So let's see if it's done. So this is one of our faders. So you would basically have that signal generator, let's say, would come into this port, and then coming out of this port, this would go to, you know, your antenna effectively. So and then you would apply the fading profiles between these two ports. Just as I mentioned, you would turn on the different models. So this one, as you can see, is relatively large. It's 64 channels. You can get these are modular, and these are configurable, so you can get, I think, as low as 8 channels or as high as 64 channels. So if you need to, you know, some of these phased arrays are pretty big, and if you really want to apply, you know, fading profiles on each one of the antenna elements, you know, you would need a 64 channel fader here. The other concept, again, we talked about field testing. So this is basically looking at, you know, what they call our Nemo handy. So this is actually a portable device that can actually provide the quality of service associated with the, you know, co-locating a device certain distance from the base station. So you could actually look at the throughput, the signal strength. So you would actually have the software tool would actually show you a you know, representation of all of the key metrics, TX power, modulation scheme, and so forth and so on, so that you can really get a good feel. So you can actually, again, just walk around in concentric circles, or you could actually do some type of mapping, you know, moving further and further away from the satellite and actually collecting the data. And then you can analyze that using what's called this Nemo handy. So this is a real popular field test device that we have available as well. And we also have a Nemo solution, which basically just allows you to look at, in many cases, MIMO. So here we're actually can simulate multiple UEs or phones to actually give you a throughput and throughput per UE metrics here that you can collect out in the field, again, moving throughout the base station area so that you could actually, you know, almost create like a mapping of the area here. In many cases, a lot of our service providers utilize these tools. You know, when you look at the coverage maps and stuff like that that you can view on T-Mobile's website or Verizon's website, a lot of those utilize these tools to actually determine, okay, you know, we got coverage, you know, 2 miles this way, you know, and so forth and so on. So these are popular tools for establishing some of those coverage maps that you see. We also have drones. So people actually, you got to remember with 5G NR, the beamforming is 3-dimensional. So not only does it do horizontal or azimuth as they call it, but it can also go vertical. Now when I say vertical, I don't mean it can point up, you know, 10,000 feet into the air. So vertical is usually, you can almost think of it as the vertical range would be similar to like a stadium, you know. So I want to get, you know, I want to make sure that I could cover, you know, the cheap seats and the expensive seats associated with this stadium. So did a lot of testing at the AT&T stadiums and all these other different stadiums to actually make sure that they had coverage within the stadium, both from a horizontal plane and a vertical plane. So the drones can actually be used to make sure that, okay, we can actually cover, you know, some of the vertical. And in many cases, some of these drones may actually utilize, you know, that communication link, you know, as part of its control. The other thing we have is our FieldFox. This is our portable box. So here we can is one of the demos that we actually provide. So this is actually a phased array antenna, and then we have a FieldFox. So we've taken this out again into a lot of stadiums, and we'll put it up on the second level, the first level, the third level, and we'll just measure the quality of service, you know, the signal strength, the modulation, all of the parameters associated to make sure that they have coverage within that stadium. And if they don't, you know, they may have to add another phased array, or they may have to change the direction and so forth and so on. This also has a GPS receiver. So you could actually characterize or create, again, another coverage map of the GPS coordinates. This has a GPS antenna built right in, so you can plot, you know, GPS, you know, power versus, you know, physical latitude and longitude locations right on and put it right into a spreadsheet. So here's some of the different EVM measurements that we make. So the SSB is the actual synchronization, the periodicity. So these are actually demodulating the signal here, and you can see some of the receive strengths and so forth and so on. So this is for a single component carrier. If you have multiple component carriers or carrier aggregation, we would also reflect that in some of these other, but typically they'll just look at one of them, and then they'll characterize it and say, okay, we may need to put an amplifier here. You know, with this type of performance, we're not going to get 256 QAM, you know, that type of deal. So again, these are all part of the quality metrics associated with establishing the proper coverage. So this is another simplified version. We have two versions. Looks like I'm missing a slide here. This is basically one of the other questions that we will actually go through. So when I talk to you, we have obviously a lot of different points of interest for testing. So the backhaul is basically used to communicate between the two base stations. So you can see here you have one node here and one node there. So in many cases, this backhaul may be based on some type of fiber optic link. You know, in order to provide all of this bandwidth up front, you got to have the backhaul to transfer the data between the base stations as well and communicate with the central office. The access network is basically what we call the link or the connection between the UE and the base station. And then one of the other new technologies, I don't know if you've heard about CV2X or heard the term, smart cars. So one of the technologies associated with that, you could think of it as instead of having a picture of a phone here, these two could actually be cars. And the scenario is this car could actually communicate with that car and give it, hey, this is where I am, this is where you are, and I want you to follow me and things like that. So you could actually utilize what's called this side link interface. And in many cases, this is just utilizing, existing technology like LTE and so forth and so on. The key differentiator is, as you can see, let's say two of these cars go through a tunnel. Well, they're not going to have, in some cases, they may not have connectivity to a base station. So this side link allows them to maintain, communication, updates between the two. So they still know how far away they are, things like that. So again, you're going to hear a lot of terms associated with what they call the side link access as well. Any questions up to this point? Anything in the chat here? Or?
Hey Brian, I'm not seeing anything in the chat.
Okay.
So I think you can move ahead. I think there's a demo coming in just a minute too. Am I remembering that correctly?
Yeah. So we have one of the things I wanted to show you is a live demo here. So this is showing an actual signal that I'm generating here. This is the 5G signal. And I just wanted to show you again some of the EVM performance associated with that. So here this is the typical metrics that you're going to be monitoring. And I did, unfortunately, I had an issue with my interfering signal. I was having a problem with that. So I apologize for that. It was working before, but today I'm having an issue. So sorry about that. But basically what you would do is this is our 5G carrier. This is 100 megahertz wide. And you can see that we got pretty good EVM here. And you could also see the flatness associated with that. And then this is showing the individual carriers for each one of the tones associated with this bandwidth. So the way it works is if you take the total number of carriers and you have a certain spacing between carriers, you just multiply that, and that gives you the physical spectrum width that you see here. So it's all math associated with that. So you can see I'm getting about 1% EVM. So when you generate your interfering signal, basically it would either be on the left or right side of this. You'll actually see that this will start to get corrupted. The dots get wider. Okay, so these are all the different, constellation points, and you could actually zoom in into these points. And if you really wanted to get an idea of, okay, is it a phase issue or an amplitude issue, you could really zoom in on that. So you can see the noise is pretty much uniform here, which is what you want. If it was moving in this direction, that would represent a phase issue, and so forth and so on. So this is showing that. And then if you, as you start to decrease the amplitude with the signal, you'll start to see the degradation in the signal to noise ratio and so forth and so on. So you can see the impact as I drop the signal level going in. You can see that the signal to noise ratio is now 30 dB instead of 40 dB, and you can really see the distortion products starting to come up. The EVM is up to 3% now, and so forth and so on. So again, when you reference that table, in many cases, the base station in the UE would actually switch. This is a 256 QAM constellation. At this point, they would probably switch once it passes that 3.5. Remember, there was that threshold, 3.5%. It would actually switch to like a 64 QAM or something like that. So just to show you some of the effects and how that the quality of the channel can be affected. So any other questions or issues?
Yeah, Brian, I'm not seeing any other questions, but I think maybe we could give it a moment. If anyone wants to see, anything else in the demo that Brian was doing, I think we could probably accommodate that. Also, if you have any questions, you can go ahead and drop that in the chat. If you feel like you have absorbed enough for the day, please note that I think a little survey will pop up when you sign out. So if you could take just a moment to fill that out, we'd certainly appreciate it. That helps us to do a better job on these events, and it helps us be more effective and more useful to you when you attend these. So I'll hang out here for a minute, Brian, but if no one has any additional questions, you can also feel free to sign off. Hey, Brian. So there is a question, and it is, can you comment on how a pulsed interfering signal would impact the signal? So I think they're talking about a pulsed signal impacting a 5G signal. Is that correct? To who the person on the chat, if you want to just comment if I got that right before we answer it, maybe. So the response is yes. So for example, like a radar, system impacting 5G communications.
Well, yeah. So the bursted signal, would almost act as an interfering signal. So the key with the pulse is you have to remember the pulsed radar. The actual pulse width in a lot of radar applications are getting narrower and narrower and narrower. So the key to remember, as that pulse width gets narrower and narrower and narrower, the frequency domain is the inverse. So you're actually occupying more bandwidth in the frequency domain. So I guess as these radar pulses are becoming narrower and narrower, there is a concern because now we're using up more of the frequency bandwidth. So you can almost think of it as, if I had a 1 millisecond pulse, I'm going to have a certain amount of bandwidth. If I have a 20 nanosecond pulse, I'm going to have substantially larger bandwidth in the frequency domain. So there is a concern with the radar, pulse width and the actual occupied bandwidth that they're going to, start interfering with some of these signals. So you need to be very conscious of that and the burst associated with that. So what'll happen is, if you start to see calls being dropped or other things, generating some type of bit error rate, we do have, the same signal generator that's generating this continuous signal here. We also have the capability to look at, pulsed radar pulses, chirps and so forth as well. So we can monitor the actual, chirp signal and see what type of impact, I don't really have a signal right now, but this would actually capture the pulse, and you can look at the quality of the pulse, if it's tilting, so forth and so on. So we can monitor pulsed RF as well simultaneously. So we could actually look at the 5G signal, and then if we had a bursted pulse, we could actually look at that as well.
Thanks, Brian. And in case anyone on the call did not notice in the chat, if you would like to ask a question live, you can also click on the green microphone that's in your panel, and that should unmute you so that if you want to ask a question using audio instead of chat, that's available to you as well. So Brian, it looks like you're pulling up another demo. Yeah.
Yeah, so just to show more of the pulse analysis that you could do. So here you could actually see the table showing all of the different, this is basically a chirp. So you could actually monitor this and the 5G. Again, you could, with this software tool, the VSA software tool, we could actually have multiple measurements, multiple simultaneous. So in addition to looking at the, this is an FMCW radar, we could also look at EVM for the 5G. That was a demo I was kind of hoping to show you, but like I said, I had some issues with the interfering signal, so I apologize for that. So please note that this can look at pulsed RF, CW, any and all signals that may be adjacent to the 5G signal.
And you can also indicate that in your survey when you sign off. If you would like us to follow up to set up a more in-depth demo of anything that you saw today, we can certainly accommodate that and do that in a more personalized setting for you. All right, Brian, I'm not seeing anything else come up on the chat. Oh, I'm sorry, go ahead.
Yeah, quick question. In one of your slides, I think in slide 2 or 3 or something like that, when you talk about the FR1 ranges, I think it's go from like 410 to about 7 gig or something like that. One of the questions is that are you worried about any out of bound emissions in that range? Because again, there's a lot of safety related frequencies or assignments in those ranges that you mentioned in FR1, i.e. GPS and some of the safety related to some of the automobile and everything else. So I'm just trying to figure out where you guys are on that, and that's all.
So I think you're talking about like adjacent power issues or adjacent carriers. So like, so the FCC allocates, bandwidth accordingly to hopefully, avoid that like if you have a GPS satellite running at 1575.42, megahertz, they're not going to sell, any bandwidth to Verizon utilizing that same frequency. So when you look at the actual bands allocated, band 13, band 5, band 1, they're specifically partitioned so that you don't have interference from other bands. One of the biggest issues, though, is things like harmonics, uncontrolled interfering signals. So a lot of customers, when they design a radio or a phone, they'll actually test it, against what they call receiver. They want to make sure that the harmonics, if you develop a phone at 3.3 gig, well, that could be a harmonic of a GPS signal. So you want to make sure that GPS signal does not what they call desensitize your receiver, and they can monitor that and filter it accordingly. So a lot of these base stations have very, very sharp filters inside the box to basically notch out any of adjacent signals, so you don't have that issue. But that is one of the, I don't know if you've heard the measurement called adjacent channel power. Are you familiar with that measurement?
No, I do not.
So they'll actually look at the main signal, and then they'll actually look at something that's directly adjacent to them and make sure that there's a certain carrier to noise ratio and nothing's being generated out of their band, basically.
All right, thank you for that. I'm just worried about that. That's something that I've run into in my line of work. So I just want to know what we're doing especially in the industry, to combat some of that.
Yep. So a lot of it has to do with the filtering and, you know, associated with the base station to make sure that, you know, there's no leakage effectively.
Power leakage to the other band, to the adjacent bands. Yeah, that's correct.
Right.
And some of these even have some requirement, right, saying that you can only transmit at this power level or something like that if you have something that is very pushing on the other side of in the adjacent band and everything else. So that does make sense.
Correct.
Okay.
So if you actually look at the they have what's called additional measurements, called ACP is one of them. So this is actually showing you, okay, this is my carrier right here in the blue, and there's a requirement that basically says you can't have anything, like when you start overdriving amplifiers or if your filter's out of alignment, right, you're gonna have what they call leakage in the out of band region. So the 3GP basically states that if you're broadcasting in this channel with this bandwidth, you can't have any signals above a certain level. So the carrier to noise, this is what they call adjacent channel. So this is one of the requirements that, you know, in order to put that phone on the network, Verizon's going to want to see this data. I want to make sure that your phone's not going to mess up, because, you know, this could be your band, you know, band 13 that this is Verizon's signal, and right next to that could be, you know, some medical ISM band or some other carrier, you know, provider, and you got to make sure that nothing leaks into those adjacent. So we have built in, this is what they call adjacent channel power. Another one is spectrum emission mask. So this is another one that shows you the actual carrier, and then anything, any type of spurs or anything that may be generated, you know, or right next to this carrier will be picked up, you know, with these measurements. And you could see the limit lines associated with that as well.
Where's the limit line? I'm sorry.
So to see the blue on there,
Yeah, okay.
That's actually a limit. So you could actually set up a margin to say, okay, I want to make sure that all of the side bands are less than 10 dB down. You could go in here and change these limits and basically specify and guarantee that everything adjacent to my carrier is at least 20 dB. You know. Yep, exactly.
Okay, I got it. Yeah, I got it now. I was just trying to look from that perspective. Thank you. I really appreciate it.
Yep.
All right, that's all I have. Thank you.
You're welcome. Good question. Any other questions or?
Hey, Brian, I'm not seeing anything else in the chat. So I think that we're probably safe to go ahead and sign off if no one else has anything else. Once again, if you are signing off, please be sure to fill out a survey just to let us know what we can do better next time, how we can make this more effective for you. And I really appreciate everyone taking the time to join us this morning. Thank you.
Thank you very much, everybody.
Thank you.
Bye-bye.
Bye.